Good morning, chemistry, and welcome to our first day of full distance learning. Today we're going to go over some notes that is going to be on stoichiometry. Now, stoichiometry is really just the word that we use to kind of talk about how we relate quantities in chemical reactions. In other words, like how much of this will react with how much of this to produce how much of this. Okay, so that's kind of what we use as a word for kind of describing that the reactions and the quantities involved in a reaction. Let's kind of go through and do a little bit of a review because the last test that we did was on balancing. And so I want to just start with a simple reaction. We're going to do a synthesis reaction of ammonia, and that's going to use some nitrogen gas. So nitrogen is a diatomic molecule. I'm going to have it in a gaseous state. And then I'm going to add to that some hydrogen gas. Okay, and so that is also going to be in a gaseous state. And that's going to form some ammonia. Now ammonia is NH3. Okay, and that's also going to be in a gaseous state. And so what we're going to do is we're going to look at how this reaction kind of works again. So if I kind of back things up a little bit, maybe to when we looked at the structure, this is our nitrogen. Okay, so nitrogen as a molecule, let's look at that. Nitrogen as an atom has 5 valence electrons. So it's going to have 1, 2, 3, 4, 5 valence electrons. And then what it does is we have another nitrogen, okay, because it bonds with itself. This is why it's diatomic. Is going to have another 5 valence electrons, and then what we do is we say, well, we're going to covalently bond, so we're going to share. So these electrons form a bond, these electrons form a bond, these electrons form a bond, and we get a molecule that looks something like this. So we have a triple bonded nitrogen. Now what has to happen is it's going to combine with some hydrogen. But if we look at hydrogen as a molecule, so again, hydrogen has 1 valence electron, and there's another hydrogen, it's going to be diatomic, and so it has 1 valence electron, so they share their valence electrons, so we create that structure as well. So this would represent the three-dimensional model for a hydrogen atom, or molecule, excuse me. Now what happens here is this reaction is going to occur, and what we're really doing in a reaction is we're breaking all of these bonds. So we know that this nitrogen is going to split apart, okay? And this nitrogen now has its 3, here I'm going to show it this way. It's going to have its 3 valence electrons that it would like to connect to. So it's trying to connect, break these bonds and connect with something else. And so what it does is it says, well, I'm going to find a hydrogen atom, molecule. I'm going to split it apart, and I'm going to take those hydrogens, and I'm going to put those in. But now if I look, this isn't quite good enough because I still have this open slot. So I need to have this thing balanced. So this is where our coefficients came in. Now, I always look at this and say anytime you have a 2 here and a 3 there, the common between a 2 and a 3 is a 6. So I'm going to make 3 here and 2 there. And then I'm going to check to make sure that this is balanced. So in other words, 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. So really, I'm going to need to have 3 of these molecules. So there's my other ones. I'm going to take those apart. All right, and then this one's going to jump on here. And so we've got our 1 ammonia molecule, and then we're going to go do the same thing here. We're going to take this guy apart, and we'll make another ammonia molecule. And now what we have here is we've got our 2 ammonia molecules. Notice I have nothing left over, so we know that this is balanced in that sense. So it took 3 of these, one of those, to make 2 of these. Okay, and so that's kind of how we looked at balanced chemical equations. Now, the reality is that this is kind of giving us an idea for quantities as well. So like if I look at what I have here, I have one of these molecules. I had 3 of these molecules and I produce 2 of these molecules. Now what we do is we start to say, well, when we start talking molecules, really we're talking in terms of number of things. Okay, and so how do we normally talk about number of things? Well, the number of molecules can always be related into moles. And so what we're really doing is we're looking at this in terms of the mole ratios. So mole ratios are really the how many to how many to how many we need. So in this case, we've got 1 mole of N2, 1 mole of nitrogen gas, will need 3 moles of hydrogen gas to produce 2 moles of ammonia gas. So we can look at these in terms of ratios. Now what I like to do is we're going to actually make these into fractional pieces. So let's go ahead and make a ratio. It's 1 mole of N2 to every 3 moles of H2. That would be an example of a mole ratio. We could also do for every 1 mole of N2, we can produce 2 moles of NH3. So that would be another example of mole ratio. And then we could also have a mole ratio of 3 moles of H2 to every 2 moles of NH3. Okay? Now remember, mole ratios, if we set up a ratio, they can go this way, or we can flip them as well, so they can go either way. Now what we're doing is we're using this in our dimensional analysis. So let's go through a kind of an example problem. Let's say I have, 15 moles of nitrogen. Okay, and I need to see, well, how many moles of hydrogen will I need? So so my question is going to be, how many moles of hydrogen will I need? Now I can set this up into a dimensional analysis problem. So I'm going to start with my 15 moles of N2, and then I'm going to lay down my domino here, and it's going to be for every one, for every 1 mole of N2, I need 3 moles of H2. And so we're just setting up our relationship, so our units are going to cross out. So again, moles of N2 cancel moles of N2. We're then going to be left with moles of H2. And so 3 times 15 is going to be our 45 moles. So that's how many moles I would need. Now what if I wanted to say, okay, how much ammonia am I going to produce? So if I have my 15 moles of N2, maybe I want to figure out how many moles of NH3 I'm going to produce. So I'm going to set that up as a problem. So I'm going to start again with my 15 moles of N2, and then I'm going to get rid of my moles of N2 and convert that into moles of NH3. And that relationship again is going to be for every 1 mole of this, I'm going to produce 2 moles of this. So that's like that, using that relationship but in reverse. And then we're going to see what we get here. So my moles of N2 cancel. So 15 times 2 is going to be 30 moles of NH3. So again, we just are kind of looking at the relationships of how we can set these up. And we can do this from any different direction because the balanced chemical equation is going to give us a mole ratio. So it gives us the ratio of the number of things okay, in relationship to each other. And so like it's a 1, 3, 2 relationship, which means we can build these things that we call mole ratios. Now this is going to be an important piece as we go through our stoichiometry. You're always going to have first the balanced chemical equation. You're going to need to then set up some ratio between the two things, and then we're going to do dimensional analysis to get to our final answer. Let's see, I think I want to go through one more example, but I wanted to make sure that you get a chance to kind of see a reaction. So we're going to do a quick little cut here to a reaction of some aluminum with some iron 3 oxide. All right, we're back after that, and I wanted to now go into that reaction itself. So again, what we did is we used some aluminum, okay? It was in a solid state. We reacted it with some iron 3 oxide, okay? So again, let's review this. Iron 3 oxide. All right, so iron is Fe. The Roman numeral tells us that it's a +3 charge. My oxygen is a -2 charge, so I'm going to need to have 2 of those and 3 of those. And that was also in a solid state. And then this is a single replacement reaction, so the aluminum is pushing the iron out, so we're going to end up with iron by itself, again as a solid. And it's then going to form our aluminum oxide. Now aluminum is also a +3, so we need 2 of those and 3 of those. Now in this case we're just going to need to have a 2 there to balance this and a 2 there to balance this, so there's our balanced chemical equation. So now let's say we are going to use a big chunk of aluminum, and I'm going to use a chunk of aluminum that's like, I don't know, let's go with 7.5 moles of it. So I've got 7.5 moles of aluminum, and I want to know how much aluminum oxide am I going to form. So I have, and this is where I'm going to write this out, I have 0.75 moles of my aluminum. I'm writing it below the point here in the balanced chemical equation. I'm going to put my question mark over here, and I want to know moles over here. So I'm using labels a lot. And that's going to be another key thing when you start to set these stoichiometry ones up. I want to go from 7.5 moles of aluminum to some number of moles of aluminum oxide. So I'm going to go back here, set up my dimensional analysis problem. So I'm going to put moles of aluminum on the bottom. I'm going to put moles of aluminum oxide on the top, and it's for every 2 of these I will produce 1 of those. So now I'm set up, so all I have to do is take my 7.5 divided by 2. Let's see, I need a calculator quick. Okay. Take my 7.5 divided by 2, so it comes out to be 3.7. I'm going to round it to 3.8 moles of aluminum oxide. Put a box around it, so now I've done my problem. So again, this is just doing some stoichiometry work, and we're using our balanced chemical equation. If you do have any questions, you can go ahead and jump on, and I will help you out with those. And you just have to finish the assigned tasks for today.